All right. Let's get started. Quick recap from last time. Start with the same basic recap we have every time. Going over what exactly the definition of a topology is. So if I have some set X, then tau, we call tau a topology on X, provided that tau has three properties. What are the three properties? Go ahead.
The empty set and all of X has to be in tau.
Right, so the empty set has to be in tau, and the entire set X has to be in tau. That's the first one. What else? Go ahead.
The intersections of all the open sets have to be an open set.
Not all of them. The intersection of finitely many open sets has to be an open set. You can only pick out finitely many from your set tau. Remember, tau could very easily have infinite things in there. So it's not that the intersection of all those things has to be an open set. It's that the intersection of any finite amount of those I take out of there, when I intersect them all together, that has to be open. So if we have U1 sub, U2 sub, dot, 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 all the way up to UN, if the set of all those sets is a subset of tau, or in other words, U1, U2, U3, dot, 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 UN are all open sets, then the intersection from I equals 1 to n of those sets has to also be in tau. So take finitely many sets out of tau, intersect them all together, the result better also be in tau. Otherwise, it's not a topology. And then the third one is related to that. This one says, now take any collection of open sets from tau you want, and its union has to also be in tau. This can be infinite, this could be finite. Any collection you want. Union them all up together must also be in there. So those were the three properties that gave us a topology. And then we have a special word for the members of a topology. We call them open sets. What does it mean to say use an open set? It means it's in our topology. If it's in our topology, it's an open set. Okay, then we introduce this notion of a basis. So sometimes talking about the entire topology is a very difficult thing to grasp. And so we instead just want to reduce it to some sort of basis that we can use to build a topology from. So a basis is like the building blocks for a topology, and oftentimes it's much easier for us to wrap our heads around the building blocks than to wrap our heads around the entire topology in one go. So that's the point of a basis. Now let's look at its exact definition. So beta is a basis on X, provided that it has two properties. One, for every little x and big X, there has to be some basis element in beta such that X is in that basis element. So every little x and big X has to show up in some basis element. So the only way that beta can be a basis for a topology on X is first, if every point of X shows up somewhere in one of beta's basis elements. Maybe it shows up in a bunch of them, but it has to show up in at least one of them. Or in other words, the union of beta always has to equal X. If we union up all the sets in beta, we better get X. Number two, let's draw this one pictorially first. What we're saying is if we have two basis elements, so here's B1, it's a basis element. Remember, basis elements are sets. They're the sets that we union together to make other open sets. So here's some basis element B1. Here's some other basis element B2. Anytime two basis elements overlap, so if they overlap, that means that there has to be some point in their overlap. Otherwise, they wouldn't have overlapped. So if two basis elements overlap, there has to be some point in there. We'll call it little x. So if two basis elements overlap, then for any point in their overlap little x, there has to be some third basis element, called B3, such that X is in B3, and B3 is a subset of B1 intersect B2. So that B3 has to be in B1, and that B3 has to be in B2. It has to show up in both sets, or in other words, it has to be in their intersection. So that's what we're going to say here. The second property is that if X is in the intersection of B1 and B2, then there must exist some other basis element, B3 and beta, such that X is in B3, and B3 is a subset of B1 intersect B2. If we had those two properties, then beta was a basis on X, and it generated a topology. What was the topology it generated? The topology it generated was the empty set. So the empty set was open. Everything in beta was open, Each basis element itself is an open set. And then any union of basis elements, any union of the b's in beta is also an open set. So once I give you a basis, how do you build a topology from a basis? You take its elements and you start unioning them together. And any way you can union them together, whatever that spits out, is part of your topology. Find some scribble space. We'll write in this dead part of the board a little bit. Give a really concrete example. Let's say that X is equal to the set A, B, C. And let's say that beta, our basis for our topology on X, is equal to the set containing the set A, comma, B, comma, C. So all the singleton sets. So here's beta, here's X. Beta is a basis for a topology on X. What topology does beta generate? It generates a topology tau. Inside that topology, by definition, is the empty set. And then any union of these things. So we can take that one by itself. So the set containing A is going to be in this topology. The set containing B is going to be in there. The set containing C is going to be in there. What else is going to be in there? The set AB, the set AC, dot, 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 and all the others. And it turns out this happened to be a basis for generating the discrete topology. So that's a concrete example of a basis. So each basis generates one and only one topology. So a basis generates one and only one topology. We're going to find out that a single topology can be generated from multiple bases. So I can have beta 1, beta 2, and beta 3 all generating the same topology, but each basis only generates one topology. Make sense? Okay. So the generated topology is the empty set. Every B in beta, all the basis elements are going to be open, and then any union of those B's is also going to be open. Now we introduce the standard topology on R. What was the standard topology on R? It's the topology you get from the basis beta equal to the set of all open intervals. So we're on R, we're on the real number line. So on the real number line, here we are, here's 0. If we look at all the points from 1 to 3, together with all the points from -2 to infinity, is that an open set on R? What do we think? Too hard of an example right out the door? Let's just say we just had this. Is the open interval from 1 to 3 an open set on R? If this is our basis, what's our basis? It's a set of all open intervals we could possibly make. So ignore this for a second. Just the open interval from 1 to 3. Is that an open set on R? Yes. How do I know? It's one of my basis elements. What are my basis elements? My basis elements are all the open intervals I could possibly make. One of my basis elements is 1 to 3. One of my basis elements is 17 to 2796.5 all over pi. Okay, there's another one. Every possible open interval you can write, those are my basis elements. And any union of those open intervals is also going to be an open set. So let's look at this again. Here's 0. If I have the points from 1 to 3, together with all the points from -1 to -4, is this an open set? Yeah, it's a union of two basis elements. That's a basis element, that's a basis element. It's the union of those two things. So it's open. What about if we would extend this all the way back to -infinity? Would it still be open? Yes, because we can union together infinitely many of those open intervals if we want. So I can take that open interval, union together with that one, union together with that one, decrementing by 1, going back as far as we want. unioning together infinitely many of them. There's nothing wrong with unioning together infinite basis elements to get your open set. Any arbitrary union of basis elements is also an open set. So when you have a basis, what are your open sets? They're the empty set, any of your basis elements, and any union of basis elements. Question, is the entire set R open in the standard topology?
Yeah.
Yeah. What do you get if you union all beta together? You get R. If you union up every possible open interval, you included every possible number. You included all of R. Let's try another one. What about this set? Let's look at the number 0, the set containing 0, union together with all the numbers between 1 and 5. Is this open? So we have the set containing 0, union together with all the numbers between 1 and 5. Open? The answer is no. Why is it no?
Because we can't, an open interval have to have more than just one thing in it, right?
Exactly. So here we are, and we're trying to include the number 0. And then we had, what was it? Did I say 1 to 5? Yeah. Okay. So we've got all these points, 1 to 5. So we've got all those. We know how to get those. That's real easy. That's a basis element. Now I need to get just the point 0. I don't want a little bit past 0. I don't want a little bit before 0. I just want 0. The problem we have is any open interval that contains 0, no matter how small you make it, is going to contain infinitely many numbers to the right of 0 and infinitely many numbers to the left of 0. If I go from negative 1 over 1,000 all the way to 1 over 1,000, so we look at all the numbers from negative 1,000 to 1,000, so we're really zooming in on 0, we still have infinite things in there. So we can never get just a set 0. What about the set 1, 2, 3? Is that open? In R. So we just have the element 1, we just have the element 2, and we just have the element 3.
Is that an open interval?
No, this is a set. This is a set containing exactly the points 1, 2, 3. So if we draw a picture of it, here's 0, here's 1, 2, 3. It is this point together with this point together with this point, and that's it. Just those 3 points. Is that an open set? No. How am I going to get just 1? Any interval I have around 1 is going to include infinitely many elements. Any interval I have around 2 is going to include infinitely many elements. Any interval I have around 3 is going to include infinitely many elements. Outside of the empty set, none of my open sets are going to be finite. They're all going to be infinite because they're unions of open intervals, and every open interval is infinite. Make sense? Let's keep playing. So we feel like we got good intuition for this one, because it's one of the examples we're going to use over and over again throughout the class. So intuition for this one's good. What about if we have all the numbers from 2 to 7, including 2? So now, on the real number line, here's 0, 1, 2, 3, 4, 5, 6, 7. So we're saying, here's 2. We're saying include 2, so fill in that dot. Going over to 7, but open circle here because we don't include 7. So everything from 2 to 7, not including 7.
Well, if we include 2, does that mean that we only have 0.2 and nothing else besides that 1.2?
Yeah, so we have 2 and everything to the right of 2 until we get to 7, but we don't include 7. So 6.99999 is in here, but 7 is not. 2 is in here, but 1.9999999 is not. So we have all the numbers from 2 to 7, including 2, not including 7. Is that an open set?
No, because no matter how small you make it, it still won't be able to just get 2.
Right. Any open interval that gets 2 is going to have to get numbers a little bit to the left of 2. So you can't ever end on just a number. Whatever the number is we're going to, we can't include it. So if we're going to 2, we can never include it in order for it to be an open interval. So 2 to 7 like this, that is, if we don't include the 2. But once we include those boundary points, it's no longer an open set. So intuition there is basically anytime if you were to graph it, if you're drawing something with a filled-in circle, no, it's not open. So that's for points by themselves or for endpoints on these intervals. It's always open, don't include that point, over to don't include that point. And then we can have as many of those as you want. That's what our open sets look like in R1. Feel like we got some good intuition for it? Okay. So then we'll move on to now the standard topology in R2. Let's go over some definitions really quick. Well, first I'll give it to you, then we'll go over this, then I'll give it to you again. So in R1, all our basis elements were open intervals from A to B. Pictorially, they look like this. Right? Don't include A, don't include B, but all the points in between them, and we filled that in on the number line. For our standard topology on R2, R2 is just a plane, like the chalkboard. Our topology is going to be the set of all open balls rather than open intervals. So an open ball is going to be we're going to draw it like that, dotted lines around a circle. It's going to be all the points inside the circle, not including the boundary. The same way that when we did our open interval, that was all the points inside the interval, not including the boundary. So it's going to be all these open balls and any union of these open balls that you can possibly make. That's going to be our standard topology on R2. Go ahead.
So what is R2 exactly? Are we just renaming the real numbers?
No, R2 is a real number plane. It's R cross R. It's all the order pairs of two real numbers. So when you represent a point in the plane, what do? When you talk about this point, you say that this has point 3, 4. You represent it as a pair of real numbers. That's what we mean by R cross R. It's all the possible order pairs of real numbers you can make. R by itself is just all the real numbers. R cross R is all the order pairs of real numbers. R to the 3 is all the ordered triplets of real numbers. And that's what we use to model a three-dimensional space. Good. So R2, these are all the points on the plane. So we're talking about the plane, and our basis elements is going to be all possible open balls. And any union of those things. Let's get intuition really quick. What about if I had a shape like this? So all the points inside, not including the boundary. Is that going to be open? Yeah. We can get open balls really close to whatever this is doing, really close to this, really close to this, da, 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 da. We can get as infinitely close as we want, doing infinitely many of these little open balls, da, 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 all the way around, unioning them up. And we can use a bunch of unions of a bunch of different open balls to perfectly get that shape. We can get infinite accuracy because we can use infinitely many of them. Because it's real easy to talk about a ball, all the points in a ball. So we're going to prove as one of the last things in this class that it turns out it doesn't really matter that we were using balls. We could have used rectangles, we could have used triangles, we could have used hearts, we could have used ovals. It's just a circle is much easier to talk about mathematically than just about any other shape in R2. So that's why balls. But good insight that, yeah, there's nothing really special about using the circles except for the fact that we can describe them easily mathematically. Let's continue getting intuition for R2. What about the half plane? So I do a dotted line and I do all the points on this half of the plane. But I don't include that line. Is that going to be an open set in R2? Yes. What if I do that, but I include this point right here? Is that going to be an open set in R2?
No.
No. There's no open ball I can create around that point. Because any open ball around that point is going to contain infinitely many points. And so I can't ever get just that point. What about if I had a hole over here and I missed a point? Can we do that?
As long as you're not getting the edge yourself.
Yeah. Missing a point, that's real easy to do. What if we include one point on the edge? So we don't have any points on the edge except for this point on the edge. Can we do that? No, because any point that includes, any open ball that includes that point on the edge is going to include infinitely many points to the left of it. Good. I think we're getting good intuition for what these sets are like. What about the whole plane? Is that going to be open? Yeah, the entire plane. Is that an open set? Yeah, union up all the balls. That gives you all of R2. Good. What about the entire plane, but I remove just one point? Is that an open set? Yeah. Simple way to think about it is we already have good intuition for the half plane is. So I do this half plane, union together with this half plane, union together with this half plane, union together with this half plane. And when it's all said and done, the only thing we would have missed is that point. Remember, any union of open sets has to be open. Okay, so enough of that. Now let's make sure we understand exactly what the basis is. So last time we ended going off on a little bit of a tangent with the Pythagorean theorem and the distance formula. I have it written here a little bit different, so I'm going to redraw the picture to help you understand the exact math I have written here. So if we have 2 points x, y, here's x, here's y. What is the distance between those points? Well, if x is a point, then it must have its left-hand coordinate, which we'll call x1, and its right-hand coordinate, which we'll call x2. And y must have its left-hand coordinate, which we'll call y1, and its right-hand coordinate, which we'll call y2. You with me? Here's a point x, here's a point y. What's the distance between them using the Pythagorean theorem? It's this distance squared plus this distance squared, all under the radical. This distance squared equals this distance squared plus this distance squared. So this distance equals the square root of this distance squared plus this distance squared. And then what is this distance? It's this one's x-coordinate minus this one's x-coordinate. So that's x1 minus y1. That's our distance here. And then square it. This distance here is x2 minus y2. That's our distance here. And so here's how we get the distance between 2 points in the plane. We often call that the Euclidean metric. Okay, so that's what I mean by the distance between x and y. You already had good intuition for it, but now there's a precise definition as to what we mean. Now, what do I mean by the ball centered at x with radius r? The open ball centered at x with radius r. What is that? So let's draw a quick picture. We're saying, here's x. We got some open ball with radius r. What is this set of points? That is all the points y and r2. So that's all the points in here. We're going to talk about a specific example of one, y. That's all the points y and r2 where the distance from x to y is less than r. It's any point whose distance from x is less than r. If your distance from x is less than r, you're going to be inside this ball. If your distance from x is exactly r, you're going to be on the perimeter here. And if your distance x is greater than r, you're going to be outside the ball completely. So this is why we use open balls, because it's really easy to describe them mathematically. What are all the points in the open ball centered at x with radius r? That's all the points y, where the distance from x to y is less than r. Okay, and now, what's our basis? For the standard topology on R2, it's a set of all open balls. It's a set of all open balls, BXR, where x is some point in R2, so you can have your ball centered at any point you want, and where your radius is some number greater than 0. No such thing as a negative radius, and no such thing as a radius of 0. If it's an open ball, its radius has to be some positive number. We have no notion of a negative radius. Okay, so that gives us our standard topology on R, any union of these open balls. including the open balls themselves, obviously. Any questions on the standard topology on R2? Think we got it? Cool. Now, remind us of a theorem that we proved last time, but throw it up here again really quick to make sure we understand. So, we proved this last time, but let's review it. Let beta be a basis on X. So if beta is a basis on X, what do we know about beta?
Every point of beta union together to get X.
Yeah, the union of beta gives us X. So for every point in big X, there must be some basis element containing it. That's the first thing we know. The second thing we know is that anytime two basis elements intersect, then there has to be a third basis element in their intersection. Right? Okay, so let beta be a basis on X. Then, and that's big X, not little x. Then U is an open set. U is in the topology generated by this basis. U is an open set if and only if, for every X in U, we can find some basis element containing that point X that's also a subset of U. So if I have some set U here, and I'm wondering, is this set open? The answer is, yes, it is open if for any point you choose in U, doesn't matter which point you pick some point little x here. If for any point X in U you choose, I can find some basis element, who knows what it looks like, I can find some basis element, this is what we mean by B sub X, containing that point, where B sub X is also a subset of U. If I can do that for every point X in U, then U is going to be open. How do I know? Because then U is going to be equal to the union of all those B sub X's. I find a B sub X for this point. I find one for this point, 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 for this point. For every point in U, I find its corresponding basis element. Union all those up, and you get U. Go ahead.
So if U is only one point, you still find a basis element that contains that one point.
So if U is an open set, and it's a single point like A, then the set containing A has to be one of your basis elements. Otherwise, U couldn't have been an open set. Because remember, what does it mean for U to be an open set? Well, when it's generated by a basis. If U is an open set generated by a basis, it has to be a union of basis elements. The only way you can get a single element set as an open set is if it was one of your basis elements. Because it has to come from unioning up basis elements. The only way I can union sets together and get a singleton set is if I was unioning a singleton set with itself. So, yes, that can happen, but that would mean that that set by itself is a basis element. Okay, so let's go over the proof. First, we're going to show that if U is an open set, if U is a set generated by the basis, then it has this property. So assume U is open. Observe that since U is a union of basis elements, that's what it means for it to be an open set when it's generated by a basis. It's a union of basis elements. Then there must exist some basis element containing any X in U. And that basis element has to be a subset of U. If U has some point X, and I know that U is a union of basis elements, then there must have been some basis element, B sub X, containing X that's a subset of U. There must have been some basis element we used in constructing U that contained the point X. So, since U is a union of basis elements, then there must have been at least one basis element, B sub X and beta, that contained X and was a subset of U, because U is a union of basis elements. So one of its basis elements that's a union of must have had X. And since U is a union of basis elements, obviously the basis element has to be a subset of U. Make sense? That's the easier direction. Now let's go the other direction. Now we're going to show that if this condition is the case, then U is open. We're going to show that if for every X in U, there exists some basis element b sub x such that x is in b sub x is a subset of u, then u is open. That's a picture I drew before because that's a harder way to get it. So if u is some set, and it has a property that for any little x in u you choose, there exists some basis element b sub x containing that point, that's also a subset of u, then u is open because it's going to be the union of all these b sub x's. I do it for when x is that point, when it's that point, when it's that point, when it's that point. We do that for every point in u. We get all the b sub x's, union them all together. That gives you u. So that's exactly what I'm going to say here. Now assume that u is a subset of x, and that for every little x in u, there exists some basis element such that x is in that basis element, and that basis element is a subset of u, not a subset of beta. That doesn't make sense. Then u is equal to the union for every little x in u of its corresponding b sub x. And so since u is equal to a union of basis elements, u is open. That's what it means to be open when you're generated by a basis, your union of basis elements. That is what our open sets are. Any questions on that? All right. Now we're going to start working up to proving that this basis right here let's see, what are we working up to proving? Oh. So far I told you that this is the basis for the standard topology on R, right? Now I need to prove that this is in fact a basis. So I've just been calling it a basis. We need to prove it's a basis. You can't just call it a basis and be done. So far you're taking my word for it that this is in fact a basis. I still need to prove that to you. I need to prove to you that it has the two properties every basis should have. So that's what we're getting ready to do here. First, I need a quick lemma to help me with that. Remember that all this is nothing. So my proof skips down to when I could halfway write again. So first we're going to do a quick lemma. Let me move the camera so I can use that scribble space. Did I get it all? Quite. Remind me. I think I will probably be good like that. Okay. Anyways. So over here, proving this lemma. What this lemma is going to say is that take any open ball centered at x. So here's x. Take any open ball centered at x with radius r. And pick any point inside that open ball you want. We're going to call that point y. So here's some random point in there, y, inside the open ball. This lemma is going to say, I can construct an open ball containing that point such that my new open ball is a subset of the entire open ball. And I'm going to construct it with some radius epsilon. So I am going to construct b sub y, or b of y epsilon, such that it's a subset of b of xr. The open ball centered at y with radius epsilon is going to be a subset of the open ball centered at x with radius r. By design, I'm going to make that happen. One thing you're going to need to know for this proof is what's called the triangle inequality. What's the triangle inequality? Here's a point A, here's a point B, here's a point C. The triangle inequality is that the distance from A to B is always less than or equal to the distance from A to C plus the distance from C to B. Or in other words, it says that the shortest distance between 2 points is a straight line. You can't pick some third point and get there faster. Well, not faster, but in a shorter distance. So it says that the distance from A to C plus the distance from C to B is always and forever less than or equal to the distance directly from A to B. That's triangle inequality. The distance from here to here plus the distance from here to here is always less than or equal to the distance from here to here for any 3 points in the plane you pick. It could be equal because you could pick 3 collinear points. I could pick this to be my point A, this to be my point B, and this to be my point C. Now the distance from A to C plus the distance from C to B is exactly equal to the distance from A to B. But there's no way for me to get a shorter path going to some third point C. There's no point C I can go to first and get a shorter path than just going straight from A to B. That's triangle inequality. That's what we'll be using in this proof. Unfortunately, we're not going to prove it. That's something you do in real analysis, so it's just not part of the scope of this class. But hopefully it's pictorially intuitive enough. Okay. So let me draw the picture for how I'm going to say this. So I'm going to start out and say, let x be any point, let r be any positive number, and consider the open ball B centered at x with radius r, and let y be any point in there, y. Now I'm going to say let epsilon be any positive number such that epsilon is less than r minus the distance from x to y. So I want epsilon, I want my radius for this thing to be less than r minus the distance from x to y. Notice that this is the distance from x to y. This is r. So r minus the distance from x to y is this distance. I don't want epsilon to go outside this circle here. So notice this is r, but this distance through here is also r. This is r. This is my distance from x to y. I want epsilon, the radius that I'm using to construct this inner ball, epsilon, I want its radius to be less than r minus d sub x. R minus the distance from x to y. Okay? So that's where that number comes from. So let's do the proof. Let x be any point in R2, let r be any positive number, and let y be any point inside the open ball centered at x with radius r. Next, let epsilon be greater than 0 and less than r minus the distance from x to y. Exactly what I said there. Now, what am I going to do? I'm going to show that this open ball is a subset of this open ball. And so it's completely contained within it. I'm trying to show that B centered at y with radius epsilon is a subset of B centered at x with radius r. That's the whole goal of the proof. How do I show that one set is a subset of another? Perfect. So I'm going to pick some arbitrary point z in here and show that it's also in here. I'm going to show that for any point you pick in this set, it's also in this set. So let z be some point in my smaller ball. Now since z, and now I say consider the distance from x to z. So now we're going to look at the distance from x to z. Let me draw this picture just a little bit bigger so that we can label everything and see exactly what's happening. So here's x, here's r, here's y, sorry, not a very good ball. Here's, maybe I'll draw it this way. Here's epsilon. And then here's some point z. And so I'm going to look at the distance from x to z. If the distance from x to z is less than r, then z has to be in this open ball. Because this is all the points whose distance from x is less than r. So if the distance from x to z is less than r, then z has to be in this open ball. You with me? Now I'm going to start by looking at, we'll squish it a little bit. I'm going to start by looking at the distance from z to x, or from x to z. Which way do I put it here? I do x to z. The distance from x to z, my whole goal is to show that my distance from x to z is less than r. First thing I do is I use my triangle inequality. I know that my distance from x to z is less than or equal to my distance from x to y plus my distance from y to z. That's the triangular equality that I told you we were going to use. Going straight there is always less than or equal to taking a detour. So this is going to be less than or equal to my distance from x to y plus my distance from y to z. Now my distance from y to z always has to be less than what number? Epsilon. Right? That's what it means for z to be in this open ball. We already know z is in this open ball. The question is it in this one? So since z is in this open ball, its distance from x to y has to be less than epsilon. So that means if we replace this, sorry, just going to erase the top of this circle. That means that this is going to be less than the distance from x to y plus epsilon. If we replace the distance from y to z with epsilon, we could have only made this number bigger. Epsilon is for sure bigger than the distance from y to z. So the distance from x to z, if it's less than this, it's definitely less than this. You with me so far? Now, what does epsilon have to be less than?
R subtract your distance from x to y.
Perfect. By definition, epsilon is a number greater than 0, but less than r minus the distance from x to y. Here's our distance from x to y. Here's r. R minus the distance from x to y is this distance. We wanted epsilon to be smaller than this distance, so it doesn't go outside the circle. So by our choice of epsilon, by definition, we said let epsilon be some number greater than 0 and less than r minus the distance from x to y. So that means that this whole thing is definitely less than d from x to y. If I replace epsilon with r minus d from x to y, I could have only made it bigger. Epsilon is for sure smaller than r minus the distance from x to y by definition of epsilon. Now, if I have the distance from x to y plus r minus the distance from x to y, what do I have? R. This is just equal to r. So I showed that the distance from x to z is less than or equal to this, is less than this, is less than this, is equal to r. Or in other words, the distance from x to z is less than r, which is what we were after. So I show that the distance from here to here is less than r, or in other words, z is in the big open ball. So that's what we say here. So then the distance from x to z is less than or equal to the distance from x to y plus, I think it's the exact same math here and here. So we just did it twice. So then y is in the ball centered at x with radius r, which tells me that the ball centered at y with radius epsilon is a subset of the ball centered at x with radius r. I just barely showed that any point z that's in here is in here. Therefore, I was able to do it. I was able to find some smaller open ball containing y. So, big picture, what did we do one more time? We just basically said that for any open ball, and for any point you pick in it, I can always find another open ball centered at that point, such that the smaller open ball is a subset of the bigger open ball. That's what we proved. With me? Okay. Now for our grand finale. Next. So that was just a lemma to help us prove our main theorem, which is that the basis, the set of all open balls, is in fact a basis. We've just been calling this a basis for the standard topology on R2. Now we're proving this is in fact a basis. So beta equal to the set of all open balls centered at x with radius r, where x is any point in the real plane and r is any positive number, is in fact a basis. That's what we're proving. So we need to show it has the two properties of a basis. The first property we need to show is that every little x in big X, or in this case, sorry, R2 is our big X, right? So observe that for every point in R2, x is in the open ball centered at x with radius 7. The ball centered at x with radius 7 is an open ball containing x. Why did I do the ball with radius 7? It's completely arbitrary. The point is, for any point x you choose, I can find an open ball containing it. The ball with radius 7. I could have just as easily chosen a ball with radius 3. There's an infinite number of basis elements I could have chosen for that x. There's one. So what did I show? I showed that for every point in R2, there is some basis element containing it. That's our first property. Now our second property. I need to show that anytime two basis elements intersect, then grab a random point in their intersection, I can find a third basis element that contains that point that is also completely in their intersection. So if I have some open ball, B1, and I have some other open ball, maybe this one's smaller like that, B2. So here's their intersection. For any point in their intersection you choose, little y here, I need to prove, probably use a little x, so let's use a little x. I need to show that there's a third basis element, a third little ball containing that point, and that third little ball has to be a subset of both these balls. Or in other words, has to be a subset of their intersection. That's what remains to show to demonstrate that this is in fact a basis. So what's our thinking going to be for this? Let's draw a slightly cleaner picture. So I have two open balls intersecting. I'm just going to draw them as full circles so that they're easier to see. But remember, they're open balls. So I've got one open ball here, one open ball here. Here's B1, here's B2. And here's some point in the intersection X. Now I know from my lemma here that I can draw some open ball around X such that this open ball, I can choose some radius. We'll call it epsilon 1. So when I construct an open ball with some radius epsilon 1, there has to be some epsilon 1, such that this open ball I construct, let's make it kind of big, so that this open ball is entirely a subset of this open ball. And there has to be some other radius I can choose, call it epsilon 2, such that the open ball using that radius is a subset of this ball. You with me? So one radius will make it a subset of this ball. Another radius will make it a subset of this ball. If I use the smaller of the two radiuses, it's going to be a subset of both balls. And so that's exactly what I'm going to do here. I'm going to say we'll use epsilon equal to the minimum of those two radiuses, epsilon 1 and epsilon 2. And then that will be the open ball. That will be a subset of both this and both this. And therefore, that's an open ball in the intersection of them. And since it's an open ball centered at X, obviously it contains the point X. So that's going to be our third basis element containing X, such that it's a subset of the first basis element and the second, or a subset of their intersection. That's a big picture of what we're doing here. So now let's go through the nitty-gritty. So we already showed that every point is, so we're right here. So let X be in the open ball centered at some point x1. So x1 is whatever point this happens to be centered at. So x1 might be the point there, and x2 is whatever this happens to be centered at, x2. And r1 is whatever this one's radius happens to be, r1, and r2 is whatever this one's radius happens to be, r2. So let X be in the intersection of my first open ball and my second open ball. And observe that there must exist epsilon 1 and epsilon 2 in the positive real numbers, such that X is in that first smaller ball is a subset of the bigger ball. So that was this one in here. There has to be some smaller ball containing X that's also a subset of this bigger ball. And similarly, there has to be epsilon 2. So this was epsilon 2. Epsilon 1 was that one. There has to be some other number, epsilon 2, such that X is in the ball with radius epsilon 2 is a subset of this ball. Let epsilon be the minimum of those. In other words, take the smaller radius of the two balls we have here. And then X will be in that smaller of the two balls, for sure. And that will be a subset of the intersection of both the bigger balls. because the smaller ball was in both of them. So it's in their intersection. Therefore, it made as a basis. We showed it has the two properties. We showed for every little x in R2, there's a basis element containing it. We showed anytime something is in the intersection of two basis elements, there was a third basis element containing it, where the third basis element was a subset of the intersection. That's the two properties we show for it being a basis. Any questions on that? Okay. Get the rest of the board for sure. So I told you that, so now we know for sure that this beta equal to a set of open balls is in fact a basis. We know that. And we know the topology that it generates is a standard topology by definition. What's a standard topology? The topology generated by this basis. That's what we mean by a standard topology on R2. Now I'm going to pick a completely different basis, and I'm going to show you that that still gives us a standard topology. So this new basis that I'm going to pick is going to be the basis of all the open rectangles. So I'm going to say if we use our basis elements to be all the open rectangles, all the rectangles you can make where we don't include the edges, but all the points in between, if that was our basis, then it still gives us a standard topology. And that's no different than using all the open balls, where we take all the points inside them, not including their boundaries. Now, notice how I represent these rectangles. It's the open interval AB crossed with the open interval CD. So let's draw that pictorially. Here's A, here's B, here's C, here's D. So the open interval AB is all the points from here to here. So that includes, let's draw these dotted lines. That's all these points. Cross it with all these points, and that gives us this rectangle. If we look at all the ordered pairs whose x-coordinate is between here and whose y-coordinate is in between here, that's all these points. So we're basically saying your x-coordinate has to be greater than A and less than B, and your y-coordinate has to be greater than C and less than D. And if you have those two restrictions on all your points, then you're in this rectangle. So that's mathematically how we describe these rectangles.
First time we're seeing that X operator.
The crossing of sets? Yeah, that's a cross product on sets. So if I have the set AB cross, oh, this might be the first time these kids are seeing it. Oh, sorry. So if we do AB crossed with the set, this is the set cross. So this isn't multiplies like on the real numbers. This is a set product. Cross product on sets. Cross with 1, 2, 3. This is equal to the set of all the ordered pairs I can make where your first element comes from this set and your second element comes from this set. So this is A1, A2, A3, B1, B2, B3.
Looks like a power set.
No. The power set is a set of all possible subsets. So you can talk about the power set of this set or the power set of this set. Okay, very different things.
Yeah.
So the real plane is R cross R. It's all the ordered pairs you could possibly make where your first element comes from this set and your second element comes from this set, which is what we mean this whole time by R2. Sorry if I didn't explain that before. That's what we mean. Okay, so take all the points from here, cross with all the points from here. That means all your x-coordinates had to come from here, and all your y-coordinates had to come from here. And so that gives us this rectangle. Make sense now? Good, good. All right, so first off, we need to prove that this is in fact the basis, is a basis, and then we need to prove that the topology it generates is a standard topology. So first, let's prove it's a basis. Observe that for all x in R2, comma, x is in the rectangle we get if I use my first coordinate, x sub 1, and I subtract 1, going to my x coordinate if you add 1, crossed with my y coordinate if you subtract 1, to, oh my goodness, sorry. I'm saying it out loud, right, but I keep writing it wrong. Crossed with my y coordinate if you subtract 1 to my y coordinate if you add 1. So let's draw pictorially what this is really quick. So here's my point x, and it has coordinate x1 comma x2. So this right here is x1, and this right here is x2. With me so far? So we're looking at the open interval x1 minus 1 to x1 plus 1. So x1 minus 1, that's somewhere over here. x1 plus 1, that's over here. x2 minus 1, that's down here. x2 plus 2, that's right here. And we're doing the cross product of these two. In other words, it's a 2 by 2 square centered at x. So for sure, x is in the 2 by 2 square centered at x. Okay, so that shows that it has the first property of a basis. Every point in every point in R2 shows up in at least one basis element. Here's a basis element containing it. I just need to pick an arbitrary basis element containing it. There's one that contains it. Okay. Next, I need to show that any intersection of two basis elements, any point in the intersection of two basis elements, has a third basis element containing it. Now, mathematically, this isn't too hard to say, but it's going to be hard for you to see what's going on. So pictorially, let's draw this out. So here's what we're going to have. We're going to have an A1 and an A2 and a B1 and a B2 and a C1 and a C2 and a D1 and a D2. So one of our basis elements is going to be A1 to B1 crossed with C1 to D1. Here's one arbitrary basis element. And another arbitrary basis element is going to be A2 to B2 crossed with C2 to D2. So here's our two arbitrary basis elements. And I'm going to draw pictorially what they might look like. So A1 to B1. We're going to want to extend each of these up, actually. But then we'll draw one rectangle at a time. Sorry, I can't draw straight lines. Okay, so A1 to B1 crossed with C1 to D1. A1 to B1 crossed with C1 to D1 is going to be this right here. Here's our first basis element. A1 to B1 crossed with C1 to D1. I'm going to shade it in this way. Remember, it doesn't include the boundary. I shouldn't have drawn it in like that, sorry. So there's our first basis element. Our second basis element is A2 to B2 crossed with C2 to D2. So it's going to be this right here. And we'll shade it in this way. So any point in their intersection, if x is in their intersection right here, notice that it is in, if I call A equal to the max of A1 and A2, B equal to the min of B1 and B2, C equal to the max of C1 and C2, and D equal to the min of D1 and D2, if that is what I call my A, my B, my C, and my D, then now X is going to be in the interval AB crossed with CD, and this interval is going to be the exact intersection of these things. And so it's a subset of the intersection of those things. So notice at the intersection, it starts at, so here's my intersection. It's this square right here, or this rectangle right here, right? Notice it starts at whatever's bigger out of A1 and A2. So it starts at the max of A1 and A2, whichever of those is bigger, and it ends at whichever one is smaller out of B1 and B2. If I would have, imagine I grabbed this rectangle here and I would have stretched that out, then now the intersection would have stopped at B2. So it stops at whichever comes first out of B1 and B2. So it starts at whatever comes second out of A1 and A2, and it ends at whatever comes first out of B1 and B2. My intersection does. Similarly, it starts at whatever comes later out of C1 and C2, and it ends at whatever comes first out of D1 and D2. So this intersection right here is going to be a basis element containing that point. Make sense? So, 2. Let X be any point in the intersection of A1 to B1 crossed with C1 to D1 intersected with A2 to B2 crossed with C2 to D2, comma, and let A equal the min of A1, A2, it's A1, comma, A2, B equal the max, whatever is bigger out of B1, comma, B2, C equal the min of C1 and C2, and D equal the max of, and D equal the max of those two things, and D equal the max of D1, comma, D2. 3, then X is in A to B crossed with C to D, which is going to be a subset of their intersection. Subset of A1 to B1 cross C1 to D1, the first rectangle intersected with the second rectangle. Cross. I should have just labeled these rectangles. I'm just going to call the first one R1 and R2. R1 intersected with R2. Where R1 is this rectangle. So this is R1, and R2 is this rectangle. This is R2. So I don't have to keep writing that out. That's getting tedious. Okay, so that was the first step. So we showed it is a basis. Now I need to show that the topology it generates is a standard topology. So for let tau be generated by beta, and let tau sub s be the standard topology. The standard topology. My job is to show that those two topologies are the same. Those two sets are the same. How do we show that two sets are equal?
We show that for every point there is in one set.
So we show that everything that's in here is in here, and the other way around. Everything that's in here is in here. Or in other words, I need to show this is a subset of this, and this is a subset of this. Now, it's pretty similar going both ways on this. So I'm just going to pick a direction. I'm going to show you that everything that's open in the standard topology is also in the topology we generate. And I'm not going to bother showing the other way. Just because it's almost the exact same thinking 2 times. All right, 5. So I need to show that everything that's in the standard topology is in tau. That's the first way I'm going to do it. So let U be some open set in the standard topology, tau sub s. Let U be some open set in the standard topology. I'm going to show it's an open set in R topology. How do I show it's an open set in R topology? I show it's a union of R basis elements. I show that you can somehow reconstruct it with a union of rectangles. How am I going to do that? If this is U, I'm going to show that for any point in U you pick, we can find some open rectangle around that point containing it, where that open rectangle is a subset of U. So we'll call that R sub x. If this is a point x, this is R sub x, some rectangle containing x. And if I can do that for every point in U, if I can show some little rectangle, if for any point in U, I can show you that I can find some rectangle around that point, where the rectangle is still a subset of U, then the union of all those rectangles is going to give me U. So that's my whole goal. We're going to take U. I'm going to say let x be some point in U. My whole job from there is to find some rectangle R sub x such that R sub x is a subset of U and contains the point. And if I can do that for any point x, the union of all those rectangles gives me U. Therefore, U is a union of rectangles. Therefore, U is generated by our basis. Therefore, U is in our topology. So I took U as something random out of the standard topology, and I showed you it's open in our topology. And then doing the reverse, taking something that's open in our topology, and showing it's also open in the standard topology, that part we're not going to do because of similar thinking. To do that one, we do what we did before. We take a U in R's, and then we show it for any point around it you can find an open ball containing it. So we're going to do the rectangle way. All right. So let U be some random set in T sub s in the standard topology. If it's in the standard topology, what do we know about it? Which basis elements? If it's in the standard topology, which basis elements is it constructed from? It's constructed from open balls. The standard topology on R2 is the topology generated from the basis of open balls. So T sub s here, tau sub s, is the set of all open sets that can be constructed using open balls. That's what we mean by the standard topology on R2. Tau here, R topology, where did I write? This tau is all the open sets you can generate using this basis. T sub s is all the open sets you can generate using this basis. I'm trying to show that those are the same thing. Whether you use this basis or this basis doesn't matter. So, U is something that you can generate using open balls. I'm going to show you can also generate using open rectangles. But so far what we know about U is it is generated using open balls. So, what am I going to do? Draw the picture one more time. Here's our U, whatever it looks like, I don't know. For any point x in U you choose, I need to show how to construct an open rectangle containing that point, where that open rectangle, R sub x, is a subset of U. That's our whole goal here. Once we've got that, we're done. And we've shown that U is also in R topology. We know it's in the standard topology. We're trying to prove it's also in R topology. Okay, so let U be something in there. What does that mean? That means that there must exist, let U be in there, comma, and let x be some random point in there. And let x in U. Since x is a point in U, I know that there must exist some open ball, B sub xr, such that X is in that open ball, and that open ball is a subset of U. So I already know if it's in the standard topology that I can construct an open ball centered at that point. How do I know centered at that point? How do I know not just an open ball containing it? So maybe I skipped a step there. I'm just using this lemma in my head that we proved, but maybe I should make that more explicit. So sorry. Let X be in U, and that must mean that there must be some open ball centered at some point, we don't know, Y, R, such that X is in, we'll call R1, because I'm going to use a different R here in a sec, such that X is in that open ball and is a subset of U. So if U is an open set in the standard topology and X is a point in there, there must be some open ball containing it. Maybe the open ball is not centered at X, maybe it's centered at some different point Y. But I know from our lemma that we proved over here that I can construct a circle around X so that that circle is a subset of that circle, and that circle is a subset of U. So I know from that then I can construct some circle so that X is in B sub X with some radius R is a subset of the open ball centered at Y with radius R1 is a subset of U. Okay, so I found a ball centered at X, containing X, where that ball is also a subset of U. Now I'm going to construct a rectangle inside that ball containing X. So zoom in what we have right here so far. So here's the edge of U, and it goes on and does whatever. Here's some edge of U. U goes on, who knows. And so far, we know that for some point X in there, I'm going to draw it kind of inside so that we can draw a ball around it. There has to be an open ball containing X, centered at X, where that open ball is completely a subset of U. Now I'm going to use that open ball to construct my rectangle. In this case, my rectangle is going to be a square, where that square is a subset of the circle and is containing X. And then that square is a subset of U. And since I can do that for every point X you choose in here, I can find one of these little squares, then U is going to be the union of all those squares. And so U is going to be a union of our basis elements. So the whole trick here is to find the square. And so a little bit of math for how do we find the square inscribed in a circle. So I already have my circle. Here's my circle. Now I need to get the square from the circle. So let's forget all this for a second, and let's just think about how we can get a square inscribed in the circle. So let's imagine I have some circle now in the xy plane, and we'll center it at the origin to help us think, and it has radius r. I want to find the points of the square inscribed in the circle. Sorry, terrible circle, but pretend that's a square inscribed in the circle. I think you know what I'm trying to draw, right? So what are the coordinates of these points going to be? That's what we're after, right? I want to know how far I need to know what these coordinates are, because then to describe the square, it's going to be these points crossed with these points. These x coordinates crossed with these y coordinates gives me that square. So that's what we're after. So I know the radius of my circle is r, so I know the distance from here to here is what? That's r. That's a radius of our circle. Now notice that this gives me a triangle right here. This is a 90 degrees. What's this angle right here? It's going to be the exact same big as this angle. Let's redraw this with just a quarter of a circle, and I think it'll make more sense. If I can draw this half decent. So we'll try just drawing a quarter of a circle. We're drawing there's a corner of our square inscribed in a circle. Not much better, is it? Here's r, our radius. If I drew this right, this would be 45 degrees. And this would be 45 degrees. So this is an isosceles triangle. So we're looking for what these x's are. I want to know how far over does this point go and how far up does it go. Obviously, it goes the same far over and up. You've almost got it.
That r squared equals x, x squared plus x squared.
X squared plus x squared, Pythagorean theorem. This side squared plus this side squared has to equal this side squared. So r squared equals x squared plus x squared. Or in other words, r squared is equal to 2x squared. Now we want to know what x is. So divide both sides by 2. So x squared is equal to r squared over 2. Or take the square root of both sides, and so x is going to be equal to the square root of r squared is just r over the square root of 2. Or we can write that as r square root of 2 over 2 if we want. I'm going to leave it this way. This is just multiplying the top and bottom by root 2. All right, we're not doing algebra, so if that confuses you, let's leave it like this. We good here? So that's my x and y coordinates. R over root 2. So now, going back to what we were after, so we have some open circle here, centered at x, with radius r, and we're looking for now this open square inside of it. X we're going to say has coordinates. X is going to have coordinates x1, x2. And so these x coordinates are going to be starting at x1. x1 is going to be right in the middle of these x coordinates. And we're going to go r over root 2 this way and r over the root 2 this way. So I'm going to be looking at x1 minus r over the square root of 2 crossed with, sorry, that's our starting point. x1 minus r over the square root of 2 is the x-coordinate for this line. And we're going to go all the way to x1 plus the r over the square root of 2. So that gives me this interval. And now I'm going to cross that with this interval. So that crossed with x2 minus r over root 2, comma, x2 plus r over root 2. So I'm going to say that this is what r sub x is equal to. So set r sub x equal to this, then that gives me that x is in r sub x is a subset of our ball is a subset of u. Right? So I just barely found some rectangle containing x that's a subset of u. How do I know that our rectangle is a subset of u? Because it's a subset of this ball, which was a subset of this ball, which is a subset of u. So it's a subset of u. So I just barely showed how for any x you choose in u, I can always find an open rectangle containing it. So 6. Then u is equal to the union for every x in u of each of those r sub x's, each of those open rectangles. It's a different rectangle for every point you pick. You pick a different point, there's going to be different circles I have to use with different radiuses. Depending on the circles I have, is going to change the rectangle I have. The closer the point is that you pick to the edge, the smaller my rectangle has to be to contain it. But take all those infinitely many rectangles, union them all up, and we're going to get u. So that gives me that our standard topology, tau sub s, is a subset of our topology. Now, I'm not going to do it, but 7, ... we would have shown that our topology is a subset of tau sub s. And this would have been the exact reverse. We would have started with the rectangle, then found a circle containing the point. We would have found a square containing each point, and then the rectangle, or the circle inscribed in the square containing the point, and then use the circles. So same idea, but rather than a square inscribed in a circle, we would have used a circle inscribed in a square. That's the same thinking. So then we get that that's equal to that, 8. Therefore, tau is equal to tau sub s. Woot. So we just barely showed, using this basis, you can also get the standard topology. So the same topology was generated by two, which seem at first very different bases. Bases. I don't know how to say the plural of that. Maybe. Those desks really slant forward, don't they? Oh, well, I won't use the whole whiteboard. All right, we still got plenty of space. Okay. Now, this notion of open balls generalizes. This is a two-dimensional open ball. Imagine we want now to talk about the standard topology on R sub n. So maybe R3, or R4, or R5, or R6. The distance formula generalizes. The distance formula, if we're just talking about in 2 dimensions, it's the difference of your x-coordinate squared plus the distance of your y-coordinate squared. If you're talking about in 3 dimensions, then it would be plus the distance in your z-coordinate squared. And if we were to talk about in 4 dimensions, then plus the distance between your t-coordinate squared. And if we were to talk about in 10 dimensions, then the difference in all your different 10 coordinates squared. Sum it all up, do the square root, Pythagorean theorem generalizes. And so does this distance formula. Make sense? So here's how you calculate the distance in an n-dimensional Euclidean space. Use that formula. So now we define our open balls. Same way. It's all the points y in Rn where the distance from x to y is less than r. So in R3, that's 3-dimensional spheres, not including their surface. So it's like all the space inside the basketball, not including the skin of the basketball. Okay, so that's what we mean by an open ball in R sub n. And then our basis for our standard topology on R sub n is just a set of all those open balls. And so you see how mathematically, talking about the standard topology on R sub 4 isn't really that much different than talking about the topology on R sub 2. It's not very hard for us to mathematically talk about 4 dimensions versus 2 dimensions. To think about it and to try and picture and imagine it, okay, that's a nightmare. I don't dare. You can try. But to describe it mathematically, that's pretty simple. Okay. Note we could also generalize our basis for open rectangles. Basis of open rectangles, beta would be A1B1 cross A2B2 cross A3C3. That would give you a volume. That would give you a rectangular prism. Cross A4D4. Now we're in 4 dimensions of space. But so you have a notion of open rectangles generalizes as well to however many dimensions. Notice that an open rectangle and an open circle, an open ball and an open rectangle are identical in 1 dimension. They're just an open interval. Okay. So now we're going to prove a theorem, theorem 1.13. But what it's going to tell us is that we can use open figures of any shape we want, including a heart, and still generate the standard topology. So we showed that you can use open circles. We showed that you can use open rectangles. Could I have used open hearts and gotten the same topology? Open diamonds, open blob shapes that look like this. Would that have still worked? I think I choose a heart because that's what the author uses. I would guess it's what he used. Because I just have it written in my notes and then I just repeat what's in my notes. I'm guessing the author gave me the idea. Oh yes, he said you could use circles, you could use diamonds, you could use hearts. Okay. Anyways, so that is what this theorem is going to give us. Let's read the theorem, understand the theorem, assume it's true, and see how it gives us that, and then actually prove the theorem. Okay, so what does theorem 13 say? Let X tau be a topological space, or in other words, let tau be a topology on X. And let beta be some collection of open sets. So far, beta is just a subset of tau. It's some collection of open sets. Then, if for all u in tau, and for every x point in each of those u's that we chose, there exists some b sub x in beta, such that x is in b sub x is a subset of u, then beta is a basis for a topology on tau. So this is basically telling us, you already have your topology, and you want to do the reverse. So we know how to go from a basis to a topology. Now I want to know how to do the reverse. You start out by giving me some topology, and I want to pick out some of the sets from it that will give me a basis. Can we do that? That's what this theorem is telling us. It says, look, pick your beta like this. Pick your beta so that for any x in any of our open sets, there exists some b sub x in your basis, such that x is in b sub x is a subset of u, then you will have for sure gotten a basis. And anything that satisfies this property, any collection of sets that satisfies this property, will give you a basis for the topology. So what is this saying we need to be able to do? So going back to standard topology on R2, we know that any shape that looks like this is an open set. And let's say that we want to take as our basis, so our beta here is going to be equal to all hearts you can possibly draw. So I don't know how to represent that mathematically, just giving you intuition here. But the set of all possible hearts you can draw in two-dimensional space. That's our basis. You with me? So this is telling us it is in fact a basis. If for any open set u, here's a random open set, and for any set x, or for any point x you pick in there, pick a random point x, doesn't matter which one. I pick this point x. If for any open set u and for any point x in u, your basis contains some set that contains that point, and it contains it in such a way, here's b sub x, and it contains it in such a way that b sub x is still a subset of u, then what you chose here is in fact a basis. And so that would mean that, okay, I can then use the hearts. If this is true, I can use the hearts. Because no matter how close you pick x to u, so you say, okay, try and draw a heart around that point. You draw it really close to the border. Well, this is just a scaling issue. Let's zoom in on that and redraw it over here. So here's our edge, and here's that point that you drew. Zooming in right there. Okay, now it's really easy for me to draw a heart around it. My heart might look awful. But so it doesn't matter. You say, oh, just pick a really, really close point. Doesn't matter. There still has to be some distance between it and the edge, because it's not on the edge. Otherwise, it wouldn't be in the set. So you can basically fit any shape in any shape if you scale it down enough. Maybe. If we, well, we don't have a proper definition of shape, and I don't know. Is a strip on the line a shape that goes on forever? Because when you try and scale down forever, you still got forever. So that's why I said maybe. So if we get a proper definition of shape, then your intuition is right. That's what I should say. Your intuition is right. Okay, so that's what this is going to tell us. So if this theorem is true, what that means is, pick your basis like all hearts. As long as it's the case, for any open set u you have and for any little x you choose in there, it's possible to use one of these things up here to capture that point. So here's our b sub x. In such a way that b sub x is still a subset of u, then you're good. So let x tau be a topological space, and let beta be a subset of tau. In our case, we chose beta to be a set of all possible hearts. Then it will in fact be a basis if for any u and tau you choose, and for any little x in u you choose, that little x right there, there exists some b sub x in beta, such that b sub x contains x. This was the same x as this x over here. Such that b sub x contains x, and b sub x is a subset of u. Then beta will in fact be a basis for our topology. So if I prove this, then you see how we could use even open hearts to get the standard topology, right? So it all comes down to, well, all right, that's big talk. Can we actually prove this thing? So let's actually prove the thing. Okay, so 1. assume that, how do you prove an implication? In general, how do we prove alpha implies beta?
That if it's true for one and then it's true for the next.
We assume the antecedent and show that implies a conclusion. If every time this is true, then this is true, then alpha implies beta. What about when alpha is false? Does alpha still imply beta? For those of you that did logic? Yes, vacuously. So we don't need to worry about the cases where alpha is false. We already got that's vacuously true. So if alpha is true, is beta true? That's all we really care about. Because the implication is always true when alpha is false. Vacuously true. Everyone always has a hard time with that one. It's one that it kind of makes sense, then you forget why it made sense, and then it kind of makes sense, and then you forget why it made sense. I have so much chalk on my hands.
I need to review that logic to break down what exactly implies is logical operator. You get a not
NAND. A NAND gate. You can use a NAND gate to create every logic circuit gate.
That's right. And I'm wondering, I was curious, what was the logical breakdown of implies if then?
In terms of NAND,
Not necessarily in terms of NAND. It was or and not.
so alpha implies beta is the same thing as not alpha or beta.
That's it. I need to make that connection.
Okay. Either alpha is false or beta is true. That's what it means for alpha to imply beta.
But if okay, yeah.
The only way you make this false
If beta's false, well, hold on.
the only way that this right here is false is when alpha is true and beta is false.
Yes, that's correct.
That's the same way, that's the only time this is false, when alpha is true and beta is false.
And so,
If alpha is false, we're good. Or if beta is true, we're good.
yeah, because all right, exactly. So yeah.
Yeah. So whatever you gotta do is make it quick with your intuition. Because it's not trivial. Or you could think through the direct proof. Sometimes we can directly prove vacuously true statements. So the one we usually do is if you let 1 equal 0, as an example of an obviously false statement, I can show this implies anything you want, as long as it's a declarative statement. Common one I give is I can prove to you I'm the Pope.
Yeah, said that one time.
Thank you. It's so hard to write a contradiction.
Nice.
If 1 is equal to 0, I can prove anything you want. I can prove I'm the Pope. If 1's equal to 0, add 1 to both sides, 2 is equal to 1. The Pope and I are 2, therefore the Pope and I are 1, therefore I am the Pope.
It's almost like it just breaks reality and therefore testing everything.
Right, so sometimes you can directly prove these vacuously true statements. If you can come up with a clever enough way to do it, but yes, false implies anything, always true. Vacuously true. All right. So, back to how do we prove an implication? How do I prove alpha implies beta? We assume the antecedent and show that implies the conclusion. So I assume alpha is true, show that implies beta is true. That means if alpha is true, beta is true. So assume, what's our antecedent here? We have if this, then this. So our antecedent is, assume that for all u in tau and for all x in u, there exists b sub x in beta such that x is in b sub x is a subset of u. So I assume the antecedent. I need to show that that implies beta is a basis. So let's prove beta is a basis. What do I need to prove about beta? First, I need to show it contains everything. Observe that the entire set X is in tau, right? And what are we assuming up here? We're assuming that for any open set, X is an open set, for any open set you choose, and for every point in it, there has to be a basis element containing that point. So X is an open set, which means that for all little x in big X, there has to exist some basis element such that X is in that basis element. And there's also a subset of X, but obviously it's a subset of X. Everything's a subset of X. X is our universe. So we proved the first thing. I showed that if your beta has this property, then it for sure satisfies the first property of a basis. Now I need to show it has the second property of a basis. You with me? So 3. Now, let little x be some point in B1 intersect B2, where B1 and B2 are basis elements. So let x be some point in the intersection of two basis elements. What do I need to show? I need to show that there's some third basis element containing that point. That's a subset of B1, B2. Remember? B1 looks something like this. They're not necessarily circles, so maybe I'll draw B2 like this. B2 could be something like this. Here's X in their intersection. I need to show that there's some other basis element, B3, containing X, where B3 is a subset of both B1 and B2. Or in other words, B3 is a subset of their intersection. It's in both of them. That's what I need to show. So let X be in this intersection of B1 and B2, where B1 and B2 are basis elements. Now notice that our basis elements were just a bunch of open sets. How did we get our basis elements? We're looking at all our open sets, and we're randomly picking out open sets, making sure that we satisfy this property as we go. So B1 is an open set, and B2 is an open set. So B1 intersected with B2 is an open set. And now we assume that for every open set in tau, and for every point in that open set, there exists some basis element containing it. So for observe that V equal to B1 intersect B2 is open, which gives me that for all x in V, there exists, we already know x is a point in V. So that means that there must exist B sub x in beta such that x is in B sub x is a subset of V. That's what we set up here. Assume that for any open set and for any point in that open set, there exists a basis element such that x is in the basis element is a subset of U. V is an open set, and x is a point in it. So there must exist some B sub x in beta such that x contains B sub x, and B sub x is a subset of V. Sorry, subset of V. But V was just equal to B1 intersect B2. So B sub x is a basis element. So we didn't call it B sub 3. I guess we called it B sub x, sorry. So B sub x is a basis element in the intersection containing the point. Okay, so we showed that beta satisfies these two properties. So beta is, in fact, a basis. Now, I think I'm missing something. I need to show that the topology that this basis generates is, in fact, that same tau. Where is his proof of this? I'm not sure how to do this off the top of my head, and I don't want to take forever thinking about it. Okay, so he calls it t prime, tau prime. So 5. Now, comma, since beta is a basis, we just barely proved that, let tau prime be the topology it generates. And it still remains to show that tau and tau prime are in fact the same topologies. That the topology we generate from our basis is the topology we chose our open sets from. Ah, something blew my page. Okay, so first direction. So I need to show that everything in here in tau is in tau prime, and then vice versa. So 6. Let U be any open set in tau. And by assumption, our very first line of the proof, and by assumption, for all x in U, comma, there exists B sub x such that x is in B sub x is a subset of U, which gives me that U is just equal to the union of all those B sub x's. So for every little x in U, get its corresponding B sub x, union them all together, and that gives us U. So U is a union of basis elements, so that gives me U is in our new topology generated by our basis, T prime, which gives me that tau is a subset of tau prime. And now I need to go the other way. So 7, now let U be some element in tau prime, and I need to show it's in tau. Since U is an element in tau prime, U is a union of basis elements. Remember, tau prime was a topology generated by our basis. So then U is equal to the union of some, we'll do B sub alpha, some arbitrary collection of basis elements, where B sub alpha is a subset of beta. So we know whatever U is, if it's in the topology generated from our basis, it has to be a union of some arbitrary collection of basis elements. Which ones, I don't know, but some arbitrary collection, union them all up, that's how we got U. But each of those basis elements, each B sub alpha, is already in tau. Our basis was composed of open sets in tau. So then U has to be a union of open sets in tau. So each B sub alpha is in tau, which gives me U is a union of open sets. Open sets in tau, which gives me that U is in tau, because any arbitrary union of open sets has to be open. Which finally gives me that tau prime is a subset of tau. 8. Therefore, tau prime is equal to tau. And we're done. We did it. So it is in fact a basis, and it does in fact give the exact same topology. So you can use any sort of basis element you want, as long as they satisfy this property, which a set of all open hearts did. Okay, so that ends it for basis elements. Next time we'll be talking about closed sets. A lot of times talking about open sets. Now what does it mean to close those things? Yeah, so we'll end it there. Any questions before we turn off the recording? Good? Okay.